Good evening. Tonight we're going to be talking about linear equations and understanding the rate of change. Now, what is a linear equation? So the fancy definition of a linear equation is as follows. A linear equation is an algebraic equation in which each term is either the constant or the product of a constant and the first power of a single variable. Now, if you're not quite sure what this means, don't worry. First, we're going to start exploring some characteristics of linear equations, and then we're going to start exploring some problems, and we're going to get a lot clearer of a picture of what's going on here. So first off, a linear equation has only one or two variables. Next, no variable in a linear equation is raised to a power greater than 1 or used as the denominator of a fraction. Lastly, when you find pairs of values that make the linear equation true and plot those pairs on a coordinate grid, all of the points for any one equation lie on the same line. Linear equations graph as straight lines. Now let's look at this example of a linear equation. Does this fit the criteria? We have y equals 4x plus 5. So, first part of the criteria is that it has one or two variables. In this case, we have x, first variable, and y, second variable. Two variables, check. Next, no variable in a linear equation is raised to a power greater than 1 or used as the denominator of a fraction. In this case, it is indeed true. The x is not part of a denominator, neither is the y, and they're both raised to the power of 1, because x to the 1 is just x, and y to the 1 is just y. Now, pairs of the values for this equation all fall on the same straight line. This is indeed true, but we will understand this when we look at the graph of some lines. First, it's important to understand what a slope is. What is the slope of the line? So I have a question. What has a larger slope, a ski mountain or a flatland? If you answered ski mountain, you are indeed correct. Now, why is this true mathematically? Well, slope is equal to the rise over the run. The rise just means it's a vertical component, and the run is the horizontal component. So, when we compute the slope, we have to compute the rise over the run. In this case, the vertical component, the rise, is going to be 6. So let's say here. The run is going to be 3. So in this case, the slope equals 2. Good. Now, we have a point-slope equation for a line. Lines can be identified by the following equation. Y equals mx plus b. But what does this mean? We have way too many variables here. Let's start making sense of what each of these variables mean. So y and x are any numbers that will work for y and x. Treat them like any other variable. M is going to be the slope of the line, and b is going to be the y-intercept. So let's imagine the line y equals 2x plus 2. In this equation, what are our m and b values? So, if y equals mx plus 2, our first m value, or the only m value I should say, is going to be 2. The b value is going to be 2 as well. So once again, this is our m, and this is our b. So how does this translate to a line on a graph? In this example, y equals 2x plus 2, the graph is shown on the right. This displays a slope of 2 because the rise over the run is 6 over 3 and a y-intercept of 2. All that means is that the line intercepts the y-axis at y equals 2. Now, we have a point on the line of -1, 0. This is what's called a solution because this point is a point on this line. So for every point on this line, there will be another solution to this equation. Let's plug this in and see how this works. So we have y equals 2x minus 2. Let's plug 0 in for y equals 2 times x, which in this case is -1, plus 2. Now, -2 plus 2 is going to be 0. So this checks out. So why is graphing lines so important? Everything from the banking system, the economy, Olympic training, computer programming, contracting, architecture, medicine, and science uses rates of change. Actually, there are infinite applications to rates of change. So let's examine in real-world terms what the previous graph means. Let's imagine this line represented our bank account. So the first day of the month, you start with $2. Now, in order to examine this, we have to understand that X is going to equal days, and Y is going to equal money. Oops. So, on day 0, we are going to start with $2. This represents our y-intercept. So that is the number we're starting with, is $2. So the next day, if we have a slope of 2, on day 1, we are going to have, or in this case, it will be day 2, we are going to have $4. Pardon the pen, it's a little slow here. Now, how much money will we have on day 40? So we can count, we can say we start with 2, and then we go up 4, and then we go up 6, and then we go up 8. Or there's a way faster way to do this. A way faster way. Try saying that 10 times. Okay, now, day 40, let's plug 40 in for x. So 40 is going to be the x. And we want to know what the y value will be, or how much money we'll have. So let's plug this into the equation. The equation again was y equals 2x plus 2. Yep. Now, let's plug 40 in for x. So y equals 2 times 40, which is 80, plus 2. So how much money will you have on day 40? You'll have $82. Now, tomorrow in class, we're going to discuss other applications of linear equations, and we'll explore more ways of using them. Now, I would like that everyone would come into class tomorrow and suggest one application that we can use linear equations for. Now, really think hard. It can be about your dieting, it can be about your exercise, it can be about your sports, it can be about your money. I want everyone to come in and give one example of how we can use linear equations. Have a great night, and I'll see you tomorrow.